we're trying to do approximations of solutions, right? You get some function and it's not a quadratic or something nice and neat. You know that there's a solution, there's a root somewhere, okay? But because it's not the kinds of functions that we know how to deal with, you can't work it out precisely, okay? But we can get very close, right? So the first method we used was the bisection method, or halving the interval. And like we said, it was very, very simple, okay? In fact, when you think about it, a function, right, and halving a method, what kind of level of understanding do you need to have? Like, what kind of mathematical chops do you need to be able to do that kind of method? Well, you need to know what a function is, okay? You need to be able to substitute stuff into that function. You need to be able to halve intervals, okay? So take averages of numbers. You think about it, when could you do that? Maybe all the way back to, say, year 8. Or year 9 if you want to be really conservative. I think, even if you don't understand what you're doing, you can teach a year 8 or 9 the bisection method. And they can go through the steps and it'll work, okay? But because it's so simple, you remember it's quite slow. Like, it took quite a few sort of steps to get any kind of level of reasonable accuracy, okay? So that's why we're going to learn Newton's method, okay? Now, Newton's method is smarter, right? That means it's a little bit harder, but it means it's a lot more accurate, a lot more quickly, okay? So what I'll do is I'll show it to you. I want you to get this down in your diagram. I'll show you the mechanics of how it works first, and then we'll look at the actual algebra and how we're going to crunch it out, okay? So here's where you start. You got your function, and you know there's a solution somewhere, okay? So you take a guess, and you need to make sure your guess is nearby, okay? For similar reasons as with bisection method, you can't just pick any values you like. I'll give you some counterexamples shortly. But suppose we pick a spot like here. Now, we'll make that my first guess, so I'll call that x1, right? So that's kind of like in the ballpark, right? So what I do with this is similar to the way I did with bisection method. I'm going to evaluate the function at that point, okay? So if I evaluate it, I'll get this. I'll have this point up here, right? Now, what will its coordinates be? Just quickly, where's it going to be at? X coordinate is x1. What's its y coordinate? F of x1. Okay, good. So far, so good. But now, here's where Newton's method gets really, really clever, okay? How are we going to use this guess to get closer to the root? Well, I told you, well, did I mention yesterday? That Newton's method involves calculus, okay? So this is not something a year 8 or 9 could do, okay? You need to be able to have a function which you can differentiate. So this is a little more narrow, it doesn't work for all functions. But you know how to differentiate tons of functions, okay? So if I can differentiate this, right? I can know the gradient at that point. More helpfully to me, geometrically, I can find the equation of the tangent that goes through there, okay? Now, why would a tangent be useful to me? Well, I'm trying to find a root. Right? I'm trying to find a solution to this equation. If you draw in the tangent at that point, at your guess, okay, what's it going to look like? Well, let's see. How well can I draw this? That's kind of close, okay? There's a tangent that goes through. We can find out the equation of this. We've been doing this for months, right? So, there's my equation. Now, what's useful about it is that where this tangent intersects with the x-axis, okay? That's going to be closer to the root than my original guess, okay? It shouldn't be further away. I mean, in this example, you can see quite clearly we're getting closer, okay? So I'm going to call this second point down here, right? I'll take this tangent, right? I'll need to get its equation. And when I solve it for y equals 0, right? That'll give me another guess, x2, okay? Now that I'm closer, I'll repeat the process, okay? So I'll evaluate it again. That'll give me this point up here, and its coordinates will be x2, f of x2, okay? And then I find the tangent through there again, right? So now, my tangent will be, let's see here. Something a little like that, right? So now, I have a third guess, right? And you can see it gets pretty close pretty quick because of the nature of the tangent, right? The idea of the tangent is, and often in some textbooks, or you'll hear some people say, you're kind of like sliding down the tangent towards an approximation, okay? And because the tangent is not just bisecting is just random. It's like, well, halfway, I don't know, like maybe that's good. But you see, the tangent is quite thoughtful. It's like, right, this should be getting me closer towards there, okay? Now, it's worth noticing that if you've got a graph, you've got a curve, and it's not concave up, right? It'll look a little different. So on the side of this, draw yourself another curve. Let's draw this one concave down, okay? It'll still work, but because of the way the tangent goes, you'll see, it's not going to be quite so neat. Still works, but. So, actually, I'm going to need a little more of this down here. Let's go a little further. Now, if I take a guess, again, let's take it to the right, okay? So, let's guess over here, x1, right? So, I evaluate, I'm going to be up here. Now, draw your tangent in, but because you're concave down, your tangent's now going to flip over to the other side of the route that you're after, okay? So, if I draw this in, it'll be something like this. Yeah, thereabouts. So I've kind of overshot, right? But because it's a tangent, assuming it's a tangent at a good spot, and we'll talk about what good spots and bad spots are in a minute. Because it's a tangent, it should be closer still, right? So my next guess, even though it's on the other side, I can still repeat this process, right? I haven't quite drawn my graph very well, so sort of mine drops off. But you can go down here, and when you draw your new tangent, the new tangent will still be closer, right? It'll be something like, I don't know, something like that. Okay, so there's going to be my x3, and you can see it gets super close, super fast. Okay, it's a great method, right? Okay, so regardless of whether you concave up or concave down, how do you do the actual maths of it? How does Newton's method actually work? Okay. So in order to go from one guess to another, what kinds of things do I need? Well, I've been talking about the tangent, right? And I said to go from this one to this one, I'm going to have to solve the equation of the tangent when y is equal to 0. So I need the equation of the tangent, right? I know the point that it goes through, okay? So what's its gradient? What is the gradient at this point? Remember, I haven't told you what the function is. I've just said it's some function. So how would you write down the gradient at that point? Yeah, good. At this particular spot, right, if you differentiate and then you put in your x1, okay, that'll give you the gradient, right? So now I know what this equation of this first tangent will be, okay? Do point gradient form. So you're going to have y minus y1. Sorry, I should have said what this is. This is the tangent at x equals x1, okay? So it'll be y minus y1. Y1 is that, f of x1. And it's equal to m outside of x minus x1. Okay, so there's our m, f dash. And x minus, now conveniently my x1 is x1. Okay, so good. There's the equation of my tangent, all right? Now remember, what I'm going to solve is, when does this tangent collide with the x-axis? That's where x2 is, okay? So therefore, this point here, right, is actually x2, 0. So I'll take those two coordinates and I'll put them in. X will equal x2, right? And y will equal 0, okay? So to find x2, I'll sub those in, okay? I'll say y is equal to 0, that's that. There's the gradient. This part here is x2, that's what I'm after, okay? Minus x1. So that's a bit messy. Let's just tidy it up. I'm trying to find x2, so let's just make that the subject, okay? So the first thing I can probably do is divide through by the gradient. That gives me this. That'll leave me with x2 minus x1 on this side. So now when I make x2 the subject, that'll become positive on the other side. Sorry, and that's still minus. Ta-da! Okay. So if I know one guess, I can go to the next one. And you can see if I wanted to do the one after that, or x3 will just be, take the previous x coordinate that you got, the previous guess that you generated. Now the way that a lot of people remember this, right, and it just proceeds from there, is that this bit on the right-hand side, what does it look like? It looks familiar, doesn't it? Looks like a derivative you're familiar with, right? This is sort of like chain rule for log functions, right? Because when you differentiate log of some function, okay, you get, what do you get? F dash on F. So that's a bit tricky. See, this is upside down. The F dash is on the bottom. I had to divide through that because this is where it was, and then to get on the other side. Okay. Did anyone think of where Newton's method breaks down? Ha! So, Newton's method relies on calculus, right? And it relies on tangents, okay? So if you find, if you have a guess, right, that's close to a place where the tangent's going to lead you somewhere else, then you're in trouble, okay? So if you're on a stationary point, it's game over, okay? Because what you'll have is, you know, there's the roots and there's a stationary point, okay, say up here. So if you're like, I'm trying to find this root, forget about this guy actually. If you pick the stationary point and you're like, okay, let's put the tangent in, it goes, whee, and you will never have an x2 because there is no, it never collides with the axis, right? But more generally, because we generally know where stationary points are, so we don't guess them, right? If you guess near a stationary point, you're still in trouble, okay? So draw this for me, okay? Suppose you have this kind of function. Okay, which is not that hard to imagine, really. And what we're trying to find is this root here, okay? Now you'd probably think, okay, I just want to be nearby, I just want to be in the neighborhood, okay? So suppose I pick a point like here. There's my first guess. Well, you can see, because of where I picked it, right, you're going to have some problems, right? Because when I draw up, right, and evaluate, that's where I want to draw a tangent through, and because I'm so close to the stationary point, right, it's not going to come back to the axis and get close to the root very quickly. In fact, it's going to be, your tangent will be so shallow that it's going to go not just further away, but closer to another root, okay? The interesting thing is, once you get this point, Newton's method still sort of works. You still arrive at something, but you won't arrive at where you want it to end, right? Because as you continue with your next guess, well actually in this case, it's going to be somewhere up there, so your next guess will be, you know, down like that, wherever it lands, okay? So you're still going to approach a root. It'll just be this one, not that one, okay? So with Newton's method, just like with bisection method, people don't generally mess up the actual calculations because it's very straightforward, very, you know, repetitive. But where people trip up is in the selection of their guesses, okay? So as with bisection method, make sure you pick one that's close enough so that you don't end up omitting roots, okay? Yes. Within reason, yeah. So yeah, like I said, often they'll give you x1, but if you have to pick it, you need to pick it nearby. You can see if I picked it over here, I'm in more trouble, right? Because I'm going further away, not closer.